Ministry of Transport, Mass Rapid Transit Authority of Thailand, GBSC Consulting Firms, Ch.Karnchang Public Company Limited presents the MRT Green Line Southbound Extension Project, Bearing-Samutprakan section. The MRT Southbound Green Line, Bearing-Samutprakan, is extended from the BTS Sukhumvit line, Mochit Bearing. Entirely built on elevated structure, the southbound Green Line has a total of 9 stations. The southbound Green Line continues from the end of BTS Sukhumvit Bearing Line and runs along Sukhumvit Road Central Reservation, past Samrong Canal. The Green Line Extension Project's first station is E15, Samrong Station, which lies between Samrong Bridge and Parak intersection. In the future, this station can be connected to the Yellow Line. The Green Line then continues past Parak and Puchao Samingprai intersections. Second, E16, Puchao Samingprai Station, is near Sukhumvit Lane 115. At the southern outer ring of road interchange, the line deviates west away from the central reservation and crosses the interchange opposite Erawan Museum before rejoining the central reservation. The third, E17 Erawan Museum Station, is located on Sukhumvit Lane 7. The fourth, E18 Naval Academy Station, is in front of the Naval Academy. The fifth, E19 Samutprakan Station, is in front of Samutprakan Polytechnic College. From this station, the line turns left along Sukhumvit Road past Sinakarin intersection. The sixth, E20 Sinakarin Station, is at Pangping Bridge, from where the line turns right along Sukhumvit Road. The seventh, E21 Praksa Station, is in front of Samutprakan School, Big C Hypermarket, and Robinson Department Store. The eighth, E22 Sailuat Station, is at Bangpu Municipal Lane 45, near Sailuat intersection. From here, the line turns left along Sukhumvit Road. The ninth, E23 National Housing Station, is at Bangpu Municipal Lane 50. Beyond this point, the track line veers westward and descends towards a maintenance depot. Total route length, 12.5 kilometers. The construction agreement consisted of 3 contracts. Contract 1, Civil Contract. The civil contract covered the construction of the elevated rail tracks, platforms, and other in-station facilities, maintenance depot, control and operation center, and a 700-unit car park building for passengers. Construction began in February 2012 and was due to be completed in November 2016. Contractor, Ch.Karnchang Public Company Limited. Contract 2, Trackwork Contract. This contract covered the designing, purchasing, installing, and testing of tracks on elevated structure, viaduct, tracks on elevated depot platform consisting of test tracks, stabling tracks, level crossings, and inspection tracks, turnouts and crossovers, buffer stops, conductor rail system. Contractor, Ch.Karnchang Public Company Limited. The above track work is presented in this video. Contract 3, Mechanical and Electrical M&E Contract. The Mass Rapid Transit Authority of Thailand signed a contract entrusting the Bangkok Metropolitan Administration with the responsibility to install the traffic signaling, controlling, and electrical systems, the supplying of carriages, and the concession process to ensure maximum convenience and uninterrupted services for passengers. The Bangkok Metropolitan Administration assigned the Bangkok Mass Transit System Public Company Limited (BTS) the operating concessionaire to perform the aforementioned tasks. On 11 April 2013, Mass Rapid Transit Authority of Thailand, MRTA, signed Contract 2, Trackwork contract, with Ch.Karnchang Public Company Limited. This contract, with the provisional sum of 2.4 billion baht, covered a period of 1,350 days and was to be fulfilled on or before 4th of January 2017. Design. The construction of the tracks and conductor rail system involved two main phases: design phase, manufacture and installation phase. Design phase. The design phase began as soon as the contract was signed. The designer was required to prepare the following information: preliminary design, PRE, stipulated the fundamental requirements for the project, as well as any references to applicable standards needed for the designing of technical details. Detailed design, DD, was the calculation and analysis of materials properties using engineering principles performed in order to conclusively decide on a proper choice of materials. Manufacture and Installation Reference Drawings, MIRD, were the detailed drawings of all the materials to be used as components of the tracks and conductor rail system. The drawings were the specifications on which production of each component would be based and served as a reference for the installation of those components. Manufacture and Installation Phase. During manufacture and installation, the manufacturer and the installer were required to prepare the following information: working drawing, WKD. This was a set of detailed drawings for the constructions. These drawings were to be followed by the installer during the installation process and to be referred to during the approval or inspection process. Final design, FID. Before completion of the installation, the designer was required to submit a job summary and a comprehensive installation report to the supervisor. As manufactured and as installed drawings, AMI. These drawings were to be made after the completion of the construction. The drawings featured the structures as actually manufactured and installed, which might differ from the original design, as could have been caused by limitations at the actual manufacture or installation site. Specifications. Main components of the track work. Running rails. The running rails, which must conform to the EN standard, shall be of the size UIC 60 with a weight of 60 kilograms per meter and a length of 25 meters per beam. The running rails are divided into two types: standard rails, or grade R260 soft head rail, shall be installed in each straight section of the line and inside the maintenance depot. Head hardened rails, or grade R350 HT rail, shall be installed in each slope, curve with the radius of curvature of no more than 400 meters, railroad switch, turnout, and station area. The railhead shall have a minimum hardness of 350 HBW and a minimum tensile strength of 1,175 neutron per millimeter square. Rail joints. Rail joints are divided into two types. Rail welding. The rails of the main tracks in every railway, switch, and in the maintenance depot shall be welded into one piece. The main track rails shall be welded using the flash butt technique. In a railway switch and the maintenance depot, where limited space rules out the use of flash butt welding instruments, the rails shall be welded using aluminothermy. However, if space permits, either flash butt welding or aluminothermic welding may be used to weld the rails in the maintenance depot. Insulated rail joints, IRJ. Insulated rail joints shall be installed on the rails inside the maintenance depot. The installation positions shall be compatible with the signaling and electrical systems. For this project, 6-bolt insulated rail joints shall be used. Check rails. In every curve with a radius of curvature of less than 200 meters, check rails shall be installed to prevent risk of derailments. The check rails shall be of the type UIC33C1 and shall be installed along the entire curve in each railway switch and at each crossing. Rail fasteners. The qualifications and life of every rail fastening component shall conform to the specifications. The required qualifications of each component are stated below. Embedded elements. Each embedded element must safely distribute the weight of the load, pressing down on the base plate. Elastic rail pads. Each elastic rail pad must be electrically insulated and installed between the rails and the base plate to reduce vibration. Non-elastic pads. Each non-elastic pad must be made of high-density polyethylene (HDPE) material, electrically insulated and capable of efficiently distributing weight from the rails to other components in the foundation. Insulators. Each insulator of the rail fastening system must be installed between the edges of the rail base and the spring clips. Spring clips. Each spring clip must be made of hardened elastic steel and capable of efficiently withstanding a load pressed down on its head. Each spring clip must undergo 3 million cycles of load testing, with the load released at the height of 2 millimeters, after which its weight-bearing capacity must not decrease by more than 10%. This project utilizes two types of rail fasteners: the 2-bolt type for straight sections and the 4-bolt type for the curved sections. The components of the rail fasteners consist of the following: dowels, concrete embedded components, intermediate plastic pads, rubber base plate pads, steel base plates, eccentric bushes, coil springs, collar washers, nylock nuts, rail pads, insulators, and spring clips. Concrete sleepers. The concrete sleepers must be of the track slab monoblock concrete sleeper type. Each sleeper must be designed to be capable of bearing up to 16.5 tons of each passenger carriage axle weight at 80 km per hour. All the sleepers with embedded rail fastening elements must be factory manufactured. In addition, the sleepers and track slabs must be fastened throughout the length of the track slabs by driving dowels through the sleepers and the track slab during the construction process. Turnouts, railroad switches, and crossovers. A turnouts or railroad switches function is to guide a train from one track to another when necessary. A turnout must be installed on a sleeper embedded in a track slab to ensure increased control and precision during installation, and enhanced quality during operation. Turnouts and crossovers consist of the following components: switch blades, switch rails. Switch blades are movable and tapering rails that direct the train into the desired track. Crossings. A crossing, a place where two sets of tracks intersect, consists of both turnouts and crossovers. A crossing, which must withstand continual impact and vibration from trains, shall be made of manganese of superior durability. Check rails. A check rail must be installed opposite the crossing on the inside of both outside tracks to prevent derailments and to guide the wheels in the correct direction. Buffer stops and wheel stops. A buffer stop shall be installed at the end of each railroad to prevent a train from overshooting. When a train hits a buffer stop, it comes to a halt without derailing. This project requires that buffer stops and wheel stops to be installed in the following areas. 1. 2 friction element buffer stops. Type 8ZEB/2 to be installed at each end of the test track. 2. 5 friction element buffer stops. Type 6 ZEB/1 to be installed at the terminals and pocket tracks. And 3. 7 wheel stops to be installed in the maintenance depot. Conductor rail system, known as the third rail. A conductor rail supplies electricity to power the train. This project utilizes the bottom contact type, which transmits electrical power through collector shoes. The main components are as follows. Conductor rail. The main material for a conductor rail is aluminum alloy, a good electricity conductor. The bottom contact material is stainless steel, which has greater wear and heat resistance. In general, each conductor rail beam is 15 meters in length. Protective cover. A protective cover is an electrically insulated material used to cover the conductor rail to keep it clean and prevent electrical short circuits. A protective cover must be made of UPVC, a long life and increased sun and rain resistance. Conductor rail ramp. The end of the conductor rail shall be fastened to a conductor rail ramp, designed to press and retain each collector shoe in the prescribed position. 2 types of conductor rail ramps are used. High-speed ramps shall be installed in the main section of the tracks and shall have a sloping ratio of 1:50. Low-speed ramps shall be installed in the maintenance depot and shall have a sloping ratio of 1:30. Conductor rail supports. Each conductor rail support must be capable of withstanding impact caused by the train's movement, acceleration, and braking. It must also be capable of bearing the weight of the conductor rails and related apparatuses. Each conductor rail support must be electrically insulated before being fastened to the ground or a concrete slab to prevent electrical current leakage and induction. Insulator assembly. To increase safety and prevent electric current leakage and induction, an electrical insulator must be installed between a conductor rail and a conductor rail support. Each insulator must be made of high-quality insulating material. Splice joints. In general, each conductor rail is 15 meters in length. The rails are to be joined with fish blades on both sides and fastened with hot bolts. Expansion joints. Because conductor rails are made of an alloy and usually installed over a long distance, an apparatus preventing damage from temperature-induced expansion or contraction is necessary. The conductor rails, therefore, must be joined with appropriate expansion joints in appropriate positions and at appropriate intervals depending on the local climate. Cable terminal or power feeder. A power supplier is an apparatus that feeds electrical power rail, connected to the cable in the cable trough. The apparatus provides an uninterrupted supply of electrical power for the train. Midpoint or anchor point fastening. At the midpoint of each expansion joint, a clamp must be fastened to the end of each of the 2 joint conductor rails to allow it to expand or contract only at the expansion joint. A level crossing is where the railway tracks and the road intersect at the same level inside the maintenance depot. This project has selected the direct fixation type, which is called CDM embedded tracks. These tracks are encased in black rubber and embedded in concrete. Track installation procedure. Inspecting and receiving the construction site based on Civil Contract 1. The survey teams determining the positions of the ground control points, the medial line between the tracks, the level of the railhead, and any other information needed for the positioning of the rail line. Transporting railway beams by trailer from the rail yard to the rail installation sites. Lifting 3 railway beams at a time onto the elevated structure viaduct using an 80-ton crane with rail lifting clamps. Lifting the mobile flash butt welding machine onto the elevated structure viaduct using 200 cranes. Installing a roller support, A-frame or rail changer set, which is used to move or lift railway beams, and necessary equipment in the welding process. Welding railway beams into 200-meter sections using the mobile flash butt welding machine, and recording all the welding information for inspection in accord with the specifications. Installing rail pulling shoes at both ends of each track to prevent wear and damage to the track's cross-section, which might otherwise be caused by impact during the moving process. Grinding the railhead, profile, and web using the rail profile grinding machine and flexible grinding machine. Pulling each 200-meter track section to the designated place using a forklift. Inspecting every welded joint using ultrasonic and magnetic particle test. After every 500 welded joints, submitting samples of welded joints to be thoroughly tested in a laboratory using radiographic test, and to be tested for durability using slow bending test. Transporting wire meshes, concrete sleepers, and rail fasteners set onto the elevated structure viaduct using a 50-ton mobile crane. Laying the first layer of wire meshes. Using a forklift and spacing chain to place the sleepers at the intervals of about 70 centimeters. Installing the fastening base plates on the concrete sleepers. Tightening the bolts with an impact wrench. Lifting and installing the tracks. Placing them on temporary sleepers and leveling them with the rail changer. Fastening the sleepers to the tracks using a movable gantry and fastening the spring clips to the tracks using a pan puller. For maximum precision and efficiency, using an automatic computerized steel binder machine to produce, bend, and cut steel binders and classify them based on their sizes and functions before transporting them to the construction site. Fastening the steel binders for the building of the derailment wall. Drilling holes for shear key installation and injecting epoxy to bond the shear key in place. After the epoxy has dried, coating the shear key with an anti-induction substance. Installing rail support jigs and tightening the track and sleeper support spindles before removing the temporary sleepers. Lining and leveling the tracks and using the spindles and lateral supports for vertical and lateral calibrations, respectively, with the reference to the specifications provided by the survey team. Performing precision checks on the following using the track gauge devices. Track gauge of 1.435 meters, can value in accord with the design, and straight section track gauge of 1.435 meters, and can value of 0. Placing concrete coverings at appropriate intervals, bending up the dowels in the concrete sleepers, attaching them to the concrete sleepers' longitudinal plates, and fastening them together with wires. Checking to ensure the steel binders for the derailment wall are fastened in accord with the working drawings, and installing and welding the stray current collector bar. Shutter boards for concrete work are designed for quick assembly, durability, and ease of use, each capable of containing the entire amount of concrete that needs to be placed. Each shutter board is equipped with plastic dowels with which to fasten the third rail support. The procedure of concrete work is as follows. Lifting the shutter boards onto the elevated structure viaduct using a 50-ton crane. Moving or distributing the shutter boards using lightweight trolleys. Drilling holes for lateral bracing support. Assembling and fastening the shutter boards. Cleaning the shutter boards and removing any residues using vacuum cleaners or high-pressure air compressor blowers. Covering the MRTH logos on the sleepers with adhesive tape. to prevent them from being stained with cement drops or other waste during concrete work. Covering the joints of the shutterboards to prolong the shutterboard's life, and the entire rail tracks with transparent plastic sheets, and covering all the rail fasteners with specially designed plywood boards to prevent them from being stained with cement drops during concrete placing. Pre-concrete placing inspection. Pre-concrete placing inspection shall be performed by the quality control personnel. The inspectors shall complete the inspection sheet before receiving concrete placing permission from the supervisor. The inspection tasks include the following: welded joints, completing the form ITPO3, flash butt welding record, aluminothermic welding record, weld joint and alignment check record. Turnouts. Every aspect of geometry and spacing bearer, completing the form ITPO4, geometry inspection and bearer spacing check and adjust record, and pre-concrete placing inspection, completing the form ITPO5, pre-concreting particulate check record, stray current corrosion control check record, stray current collector control continuity test record, sleeper spacing record, bracket for conductor rail record, line and level. Concrete placing. When each concrete mixer arrives, the concrete shall first be inspected through the following procedure: performing a slump test, recording the concrete's temperature, and collecting sample concrete coverings for a compressive strength test. Wetting the surface before placing the concrete to prevent the concrete's moisture from being absorbed. Using a mobile crane to lift concrete buckets, or using a concrete pump to move the concrete onto the elevated structure via duct, depending on the site space and condition. Shaking the concrete using a concrete vibrator to eliminate air bubbles and to ensure equal density. Leveling the concrete using a screed. Placing concrete to form the derailment wall using a concrete wagon, and shaking the concrete using a concrete vibrator to eliminate air bubbles and to ensure equal density. Smoothing the concrete surface and installing PVC chamfers. Removing any stains using a sponge. Plastering and finishing the concrete surface with finishing trowels. When the concrete has begun to set, spraying the concrete with concrete curing substance to delay evaporation of moisture from the concrete and to maximize its development of strength. When the concrete strength is fully developed, removing the shutterboards and the spindles. Grinding and cleaning the surface with wire brushes. Collecting the shutterboards and all the equipment and moving them onto the trolleys to be moved to the next work area. Grinding the chamfers and plastering all the concrete surfaces, and removing any residues and cleaning up the area. Turnout and crossing installation procedure. The installation of turnouts is similar to that of the normal rail tracks, but with thorough inspection of the switch blades added. After the switch blades have been installed, all the track sections shall be connected using the aluminothermic welding technique. Aluminothermic welding procedure. Grinding and cleaning the rail head profile, verifying the precision of the track line, setting the space, position, and track line in keeping with the rail welding requirements, assembling the molds, filling the gaps between the molds with luting paste, preheating UIC 60 rails for 6 minutes, assembling the one-shot crucible type welding powder bucket, starting a fire to heat the crucible, waiting for a chemical reaction, shearing the welded joints with a rail shearing machine, grinding the rail head using the rail profile grinding machine, grinding the rail foot and web with the rail flexible grinding machine, and cleaning and inspecting the welded joints based on the flash butt welding method. Procedure for installation of CDM embedded track type level crossing. Cleaning the installation area. Polishing the rail surface to remove rust and residues. Applying the CDM fixed glue and adhering the rubber encapsulation to the rail webs on both sides. Fastening with plastic straps. Lifting the rails into position with the rail changer. Fastening the rails with the support CDM jig at 3-meter intervals. Having the survey team adjust and verify the rail's position, and filling the level crossing area with concrete, leveling and finishing the concrete surface, and curing the concrete using a concrete curing substance. Buffer stop and wheel stop installation procedure. Designating the installation areas. Moving the buffer stops to the installation areas. Moving the buffer stops into position and fastening them with guide claws. Installing friction elements. Tightening the nuts and bolts using a torque wrench following the specifications below. Buffer stops. 250 Newton-made for each guide claw and 150 Newton-made for each friction element. Wheel stops. 150 Newton-made for each friction element and 160 Newton-made for each wheel stop. Insulated rail joint installation procedure. 1. Grinding to clean the rail head and sandblasting it. 2. Measuring and recording pre-installation electrical resistance. 3. Installing end posts and adjusting track spacing and line in keeping with the specifications. 4. Heating the railhead to 155 to 160 degrees Celsius for the bonding agent to be the most effective and checking the temperature with an infrared thermometer. 5. Spraying the primer on the rail web's contact surface. 6. Installing the adhesive insulator set, fish plates, and insulating bushes, and screwing in the bolts. 7. Measuring and recording post installation, electrical resistance. 8. Tightening the bolts with a torque wrench at 1300 Newton-made. And 9. Waiting for the bonding agent to set and sealing the gaps with liquid polyurethane. Conductor rail installation procedure. 1. Preparing and designating the installation areas based on the working drawings and fitting the dowels during the concrete placing step. 2. Fitting the bracket base to the concrete wall with an HDPE sheet inserted between the bracket base and the concrete wall to prevent electric current leakage. 3. Tightening the screw spikes with a torque wrench at 200 to 250 Newton-made. 4. Fitting the bracket support and tightening the bolt with a torque wrench at 80 Newton-made. 5. Installing the insulator assembly set. 6. Checking and correcting the position using the rail setting gauge and locking the bolts with a torque wrench at 80 Newton-made. 7. Transporting and lifting the ram elements into position and fitting them to the bracket base with jaws. 8. Transporting and lifting the 15-meter conductor rails using the conductor rail gantry crane and fastening the rails to the bracket base using jaws. 9. At each joint between conductor rails, drilling holes with a rail drill and adjusting them in the best position to be fitted with splice joint assemblies and fastening them with hug bolts. Also cleaning and greasing the contact surfaces of both the conductor rails and splice joint assemblies to prevent corrosion. 10. Installing the expansion joints whose internal structure contains the factory-installed insulated rail assembly. During installation, joint spacing must be set based on the conductor's rail temperature and the installation time. 11. Adjusting and correcting the installation position using the track gauge with a difference of no more than 5 mm from the required positions, both vertically and horizontally. 12. After achieving the correct position, installing a midpoint anchor rail in the middle of each expansion joint by drilling holes in the conductor rail in the positions indicated by the middle point anchor rail drill jig, and fastening the anchor rail to the conductor rail with hug bolts. 13. Installing a cable feed connector by drilling holes in the conductor rail in the positions indicated by the middle point anchor rail drill jig, and fastening the cable feed connector to the conductor rail with hug bolts. 14. Installing the protective covers and checking them with the structure gauge. And 15. Checking electrical resistance using a digital mega ohmmeter and checking electrical continuity using a digital micro-ohmmeter. Rail distressing. Distressing is a process of reducing a rail stress that might have accumulated as a result of fitting it to fasteners at inappropriate temperatures. Distressing is necessary because it prevents the rail from arcing when it expands. For this project, the stress-free temperature is 45 degrees Celsius. The entire length of the rails shall be distressed, divided into 500 to 1000 meter sections. Distressing is normally done during morning or night hours when the rail temperature is below 45 degrees Celsius. Distressing can be done with greater ease when the rail contracts in a low temperature. The distressing procedure is as follows. 1. Designating the points and sections to be distressed. 2. Measuring rail's temperature using a magnetic rail thermometer attached to the rail web. 3. Removing rail fasteners. 4. Lifting the rail with a rail lifting jack and placing a rail support roller under the rail at every 15 to 20 sleepers. 5. Cutting the rail at the median point with the rail cutting machine and leaving the rail to contract. 6. Striking the rail web using the rail striking machine to release the rail stress and to let it fully contract. 7. Calculating the rail's expended length by comparing it with its length in the stress-free temperature. The difference indicates the length that the rail needs to be cut off. 8. Fitting a rail tensor to place the rails in correct position for welding, and welding the rails using the aluminothermic welding technique. 9. After welding, removing the rail support roller, adjusting the rails in correct position and fastening the rails. 10. After the welded joints cool and the fasteners refitted, removing the rail tensor. And 11. Grinding and smoothing the welded joints. Rail skim grinding. When rail installation has been completed, before handing over the work, all the rails under this project's responsibility must undergo rail head grinding and polishing. This step ensures that the surface that comes into contact with the train's wheels is shiny and even and smooth. The rail surface coarseness, measured every 50 millimeters, must not exceed 10 micrometers. Rail head grinding shall be done using the computerized rail grinding machine ROV 149.3. The grinding area begins at 14 millimeters below the midpoint of the rail top on the contact side to 14 millimeters below the midpoint of the rail top on the opposite side. The smoothness of the rail surface shall be tested in accord with specifications using Kepler KR 3100 roughness tester. A minimum of 5 points per kilometer shall be randomly selected for testing. Visual inspection shall also be performed to ensure that the rail surface is shiny and well finished. There is no gap in any welded joint after each grinding, and the rail surface is even and smooth. In addition, at every 250 meters, the cross-section of the rail must be checked using the UIC 60 E1 rail template to confirm that the rail has developed no excessive deformity after grinding and polishing. System integrated testing and commissioning. The final rail installation process, which is to coincide with the mechanical and electrical component M&E contract, comprises the following. 1. Structure and clearance gauging. 2. Running rail inspection. The rail's general condition based on the installation standards. The railroad switches, turnouts. The rail's electric resistance. The structure's earth resistance. The rails and the structure's earth resistance. and the rail joins between the extension project's tracks and the BTS's tracks based on the Trackwork standards. 3. Conductor rail. Third rail inspection. The conductor rail's general condition based on the installation standards. The conductor rail's conductivity. Electric current isolation between the running rail and the conductor rail. And the condition and insulativity of the insulated rail joints. As the MRTA commissioned a high potential and high standard contractor to construct the southbound Green Line, Bearing-Samutprakan, the construction was completed as scheduled. Ch.Karnchang Public Company Limited, the contractor, paid close attention to every minutest detail and step during construction process. The work was of high quality and was so well managed that it was completed as scheduled. The personnel possessed both experience and expertise and were equipped with machinery of modern technology. The design and the selection of materials and instruments conformed to universal standards and contractual specifications, and every step of the work was transparent and inspectable. Concern about the staff's motorist and pedestrian safety was the company's priority. Negative environmental effects, whether noise, dust, or vibrations from the constructions, were kept to a minimum. During the construction, efficient traffic management ensured minimum negative effects on the inhabitants along with the track construction line. With all the above accomplishments, the construction of the southbound Green Line Bearing-Samutprakan, as conditioned in Contract 2, was completed as scheduled and met the standard requirements. This line now serves as a convenient alternative mode of transport that efficiently reduces traffic congestions and travel time between Bangkok and Samutprakan. Enhancing Thai entrepreneurs' long-term potential, this public transport system plays an essential part in attracting international investors and lifting people's standards of living.